let's move on to the next speaker. He is head of department for production integrated non-destructive testing at Fraunhofer Institute in Saarbrücken in Germany. The title of the presentation is Cognitive Non-Destructive Sensor Systems for Monitoring and Optimization of Sheet Metal Processing. I'm happy to give the stage to Dr. Bernd Wolter at Fraunhofer Institute for Non-Destructive Testing.
Yeah, thank you very much, Ingela, for this kind introduction. Good morning, ladies and gentlemen. I hope you enjoyed your coffee break. Even it was without the usual coffee break discussions. So in my presentation, I will talk about non-destructive testing, and I will show you some sensor system which we are using at the Institute. But let me start the presentation by just a moment. Doesn't work. The clicker does. Okay. No. Okay. See the next slide. First, I would like to show you from which institute I'm from or where I'm from. So it's the Fraunhofer Institute for Non-Destructive Testing. We are one of the 72 Fraunhofer Institutes for applied research in Germany. You probably know this research organization. And our institute was funded already in 1972, especially for development of non-destructive testing methods for nuclear power plants. But yeah, you can imagine. Meanwhile, our task have been changed dramatically. Our institute develops methods for non-destructive testing, NDT, and for the entire value chain. That means we really start by developing NDT techniques for materials, for new products. We go into production with our NDT systems, and then later we are using these techniques also for the end of life of a component. That means for disposal and also for recycling, for example, for material sorting during recycling. We use these techniques, these NDT techniques, in order to monitor and control quality and reliability of products and processes. And we can access a wide range of sensor systems. That means we really have the entire world of NDT, which we are working with. I'll try this again. I think I have. Okay, now it works. Okay. Okay. Nowadays, our institute is facing tremendous changes because the role of NDT is changing drastically. So I have tried to explain this a little bit on this slide. In the past, the only task for NDT was to generate quality-related data about the inspected asset by using sensors. But now, meanwhile, these sensors are also used, or the data are further processed in order to generate information. And that means we try to answer this question, not only what is the quality of the asset, but also answer the question, why does it have this quality? What are the causes and the effects of the sensed quality? And if we then compare this information, that was one too much, with historic data, we can create knowledge from this. And finally, this knowledge can be also used to support decision processes, for example, by using the NDT data for control loop. But for us, so let's say for the researchers in the framework of NDT, that means we need additional skills, not only about sensor physics and measuring technology, we need competences in material science, in production engineering, in scientific computing and artificial intelligence. We at IZFP we are engaged in further development of interfaces, for example, OPC UR, and for IIoT devices. And we are working more and more with embedded sensors for structural health monitoring of components. Okay, good. But now let me come back to the actual topic of my presentation. And this is about sheet metal processing. You see on this slide a typical, let's say, production chain in sheet metal processing, starting from the decoiling, the leveling, the planking of the sheets. Then in hot forming, you have to heat the sheets. Then you form the sheets. They are cutted. And finally, you go from the pressing plant to the body shop, and then the sheets are welded in the car body. And in all these stages, you have different issues for quality. That means, for example, after leveling, you ask about, or you could ask, or often ask about residual stress. After planking, you ask about what is about the formability of this individual plank. If you make hot forming, then you ask after the furnace process about the diffusion layer. After forming, it's clear you have to detect defects and also the properties of the components which have been formed. After cutting, often the question is about the cutting edges. What is the quality of the cutting edges? And later, clear if you are welding or joining the component, the question is about welding defects. And what I can say is that meanwhile, and in addition, I think it's a relatively new task. You have to identify this individual sheets over the entire production chain. And what I can say, meanwhile, we have developed NDT solutions for all these tasks. Because my time is limited, I cannot show you examples for all of this, but you can later ask me, and then we can look for that. So that means in the rest of this presentation, I would like to show you some of the examples. And I think a very powerful sensor technique we have developed at IZFP is the so-called 3MA sensor. It's it's a combination of micromagnetic methods. What is micromagnetic method? A micromagnetic method uses the correlation between magnetic and mechanical properties in the material. And we can measure the magnetic properties, and by that we can indirectly determine the mechanical properties like hardness and strength and so on. And the unique feature of 3MA is now that we combine several of these micromagnetic techniques in order to be able to determine then also quantitative values and to suppress distortions like temperature, batch variations, and so on. And meanwhile, we are very successful with these techniques in hot forming. We have developed a special application for these parts. We determine quantitative values of hardness, tensile strength, yield strength, elongation, and also the layer, the diffusion and coating layer thickness of these materials non-destructively. And you can imagine that the effort for testing is significantly reduced. And also very often question, how is the accuracy? What is the uncertainty of this method? And we have tested this, we have proved this, and we have seen that it's comparable to the destructive testing methods. And now we have seen that this technique can be used after forming, but I think at the moment, and it's much more interesting, is to use it before forming, because you can get information about the formability. You can see you have here a single plank, cold forming plank, and this blank should be formed then later. And you can determine before the forming process, for example, tensile strength, yield strength, elongation, and an R value after this calibration non-destructively. And with this information, you can say something about the formability of this sheet. Is it possible to form it without any defects? If not, you can scrap it directly. And if it's formable, you can select the optimum forming parameters from this individual, let's say, information about the formability properties of this sheet. And you can do it even one step before, directly during the production of the coil. That means we have already implemented such sensor systems in the production line of steel coils, and that means it's possible to continuously measure the entire coil related to its mechanical properties like strength and so on. But this is then the task for the steel producer and not for the former. And now let's come back to the forming process. It's clear after forming, it is necessary, or often it's necessary to inspect the parts if they are free of defects. And typical defects could be cracks, but also you have sometimes so-called neckings or thinnings of the material. Typically, if you have a strong elongation but no crack so far, and perhaps you know that such, especially such neckings, are very difficult to detect because you do not see it good in an optical image. And for this testing, we have developed a special technique which is called electromagnetic acoustic transducer. I do not want to explain too much the physics of the system, but you can generate ultrasonic waves with this system without any coupling to the material, and you can use then the systems. Just a moment. Okay, can you go to the next slide, please? Okay, perfect. Thank you. And now you can apply such a sensor system on one position of your formed component, and then you generate an ultrasonic wave. This wave travels through the material, and if you then have a necking or crack anywhere in the material, then you can detect it. And even small neckings, which are very hardly visible, can be detected with this method. Next slide, please. Yeah, now we go one step further. We come from the pressing plant then to the joining, to the welding. Here we have also developed sensor systems. One development route at the moment goes in the direction in order to realize an in-process detection, and one possibility is to integrate ultrasound sensors directly in the welding gun of such a resistant spot welding machine. And please go further. And what we are doing then with these ultrasonic sensors, we generate an ultrasonic wave which is transmitted through the welding spot during the welding process. And by that way, next, please, we can then determine the spot size during the welding process. Now, this is a very good method, but you can imagine that's not always possible to implement or integrate such a sensor in a welding gun because they're expensive. And for that reason, in most cases, a post-process monitoring is the more acceptable solution. And what you see here is, again, the FreeMA technique, which was used and post-processed in order to determine the welding spot diameter. And the interesting fact is these are relatively new results is that it works for double sheet welds, but also for triple sheet welds. It means that you have two welding points which can be determined then with this method. And we have seen that it seems to be possible to distinguish fusion welds and normal fusion welds, good welds, and cold welds without any fusion. That also makes a difference in the signals. Next slide, please. Now we come to a relatively new research project, and that's about material fingerprinting. That means the task is that we want to develop methods for component identification over the entire over the entire value chain of the sheet processing. And perhaps usually you are working with markers, but we think in future it's not necessary anymore to use markers. We have developed a sensor system which determines electromagnetic materials or electromagnetic material properties of the sheet. Can you go further, please? And this information is then combined with machine learning. Further, please. And by that way, we can generate some kind of material fingerprint of the component. I will show you examples of on the next slide, please. What you see here are, let's say, electromagnetic images of a sheet component, metal sheet component, of a small range of the sheet component. And the first two pictures on the left show the material, and after plastic deformation, you see the right picture, and it still works. That means you can identify also the material again after plastic deformation. Okay, and the next slide I skipped then, and I come to the conclusion. And you have seen new sensors give new application possibilities. We have sensors for form parts and for also for the coils and the planks in order to make a feed-forward control. We have sensors for forming defects, welding defects, and also relatively new for part identification. We think there's a growing need for cognitive sensor systems in future. And next point, please, we keep pushing. And with these words, next slide, please. I would like to thank you for your attention, and sorry for the small technical problems, but I think so far everything is working perfect. Thank you again for the assistance from Techtank.
So,
yeah.
Thank you, Dr. Wolter. Thank you, Dr. Wolter. Now I see myself. Thank you very much for your very interesting presentation on all types of quality assurance methods. And do you see any new surfaces? Now I have actually a question from the audience here. So let's take one. The 3MA and the EMAT sensors, I assume this method is only applicable for magnetic materials. For example, not, for example, for austenitic stainless steel.
Yes, that's partly correct. The 3MA technique really only works on ferromagnetic material. But meanwhile, we are developing also a method which can be which is working on non-magnetic, diamagnetic, electrical conductive materials. And the EMAT sensor does not need ferromagnetic material. It works also on electric conductive materials. So that means you can also use EMAT for example, stainless steels or aluminum. That's already possible. But 3MA, you are right, so far only for ferromagnetic materials. Yeah.
So thank you very much again, Dr. Wolter. And I see there's a lot of questions now. So I do hope that people who get these questions want to come to the question and answer session together with Dr. Wolter. And we will also channel these questions to your Q&A session to the moderator. So thank you again. It was a fantastic presentation.
Thank you.